Hey everybody, this is the 2012 AP Calc BC test, question number 6. So question number 6 is basically about a Maclaurin series, this series in particular. So let's just get straight into it. So A is, using the ratio test, determine the interval convergence of the Maclaurin series for G. So this problem is pretty straightforward. So we know that our A of n equals to this right here. And we know that the ratio test is essentially the limit of n goes to infinity, absolute value is very important, of a of n plus 1 over a of n. And so, when applying this to the series G, we get limit of n goes to infinity, and we replace n with n plus 1, which gives us this right here. And so one tip I have is that when it comes time for problems that use a ratio test, when negative 1 becomes negative 1 to the n plus 1, I prefer to write it expanded out so it's easier to cross out values later on. So put the absolute value sign. So this becomes x to the 2 and x to the third over 2n plus 5. And now we need to do a of n. So this becomes x2n x, negative 1 to the n, and then over times. So this is just the expanded form of the ratio test. And so we can start canceling out terms. So this cancels out, this cancels out. This becomes x to the q, x squared, sorry. And this negative 1 just gets canceled out because it is a absolute value. So now we get limit n goes into infinity of x squared times 2n plus 3 over 2n plus 5. And since we're testing for the interval convergence, has to be less than 1. And so when solving for this limit, since these are the same coefficient and these two are both to the first power, this just cancels out to 1. This becomes 1. So that means this equals x squared, absolute value of x squared, less than 1. And we can derive our interval negative 1 to 1. So fair warning right here, if you stop right here, you're essentially only getting 3 out of 5 points according to the AP rubric. And this is not what we want, unfortunately. So to get that 5 out of 5, that hundo, we have to test for these endpoints because we don't know. We do not know if they converge or not at these endpoints. So one way to test for it is to just sub in the values. So we can sub in, let's sub in 1 first. So this becomes I'll bring it right here. So this becomes so 1 to the 2n plus 1 will always be 1. So we can just write 1, 2n plus 3. So now at this point, we can see that this right here, the negative 1 to the n, makes it alternating. And we know this right here, this is technically our b of n because b of n equals the absolute value of a of n. Our b of n always decreases. And this is because 2n plus 3 is always greater than 1 along our interval from 0 to infinity, essentially. And so because we know these two, we can, AST can be applied. So AST, and so that's basically the limit, n goes into infinity, of b of n, which we have said is just the absolute value of a of n. And so since this equals 0, this actually converges. And now we're going to write basically our little paragraph describing what we did. So we say, since A of n is alternating and decreases, and the limit of b of n equals 0, A of n must converge. Just like that. And so, since we know that 1 converges, we can put 1 in a bracket. But we still need a test for -1. We don't know -1, right? But it is actually pretty straightforward, because -1, when we plug in -1 to the series, we just get n plus 1 times. And this is because -1 is basically just -1 to the first power. So this just adds together. And this is basically the same thing as if we plug in 1, because this makes it alternating, and b of n is always decreasing, which basically means our same explanation for this one applies. So that means that our interval convergence is from -1 to 1 in brackets, because they both converge. And one tip is that remember to write out your explanations, like these explanations, write out alternating, decreases, so the readers know what you're talking about, so you really convey that you understand what you're doing. And so with this, you would get a 5 out of 5. Smiley face. Now let's move on to part B. Okay, so part B is a little bit different. It's so let's just go through it. The Maclaurin series for G evaluated at x equals 1/2 is an alternating series. Alternating series is important, whose terms are decrease in absolute value to 0, the approximation. So we're trying to prove that the approximation using the first two non-zero terms, is less than 1/200. So we know from the question itself that the series alternates and decreases, meaning that AST error can be applied. And so AST error is basically when it's basically R of n, the error at the nth term, equals A of n to the n plus 1. So since we're trying to find the error of the first, we're trying to prove that the error of the first non-zero two terms is less than 1/200. So it's just R of 2 equals A of 3. And so bringing our expanded values out as courtesy of College Board, we see that the series equals x to the 3, and x over 3 cubed over 5 plus x to the 5th over 7, and on and on. But we only need these 3 terms. So what we can see is that A of 3, and we evaluate at x equals 1/2. So we plug in 1/2 to here. That is 1/32 times 1/7, because we're drawing this to right here. And so we're trying to prove that this right here is less than 1/200, which, when simplifying out, this equals 1/224, 200. So we can say that since the series is alternating and decreases, AST error can be applied. And so I'm going to skip ahead for time's sake, and I'll come back when I've written this entire thing. So now I'm just briefly, I just filled in the paragraph. So I just said, because the third term is less than 1/200, then the error of the approximation of G g to the 1/2 using two terms must be less than 1 over 200, which we're trying to prove. And so finally, we're moving to part C. Okay, so part C is also pretty simple. We're just writing the first three non-zero terms. Non-zero terms for g prime of x. So let's just write out the sequence. I'm sorry, the expanded series. So this we're already given this. So if we take the derivative of this, so this pretty much results in this right here. But we only need the first three non-zero terms, so it's right here. And then we need to find the Maclaurin series. And so because we can see that it is, so because we can see this is alternating, we can just add that in real quick. You see this is increasing by 2s, this is also increasing by 2s, but this is starting at 1 and this is starting at 3. So we can say 1 plus 2n over 3 plus 2n. And so that is in parentheses. And then finally, we can see it increased from x to the 0 to x cubed, no, to x squared, and then x to the 4th. So we can do x to the 2n. And this is just g prime of x. Okay, so that concludes question 6. And if you guys found this useful, or you want to practice other problems, other problems that are really good, that are similar to this, are some practice problems in 11.11 and 11.10. And for the error and solving for convergence, 11.5 questions 2 through 20 and 27 through 30 are also great selections. And if you just want to practice Taylor and Maclaurin series that are similar to the AP style, then the question 6 on most BC tests are also very good. Okay, and thank you for listening.